Evaluating a modern AI agent based on a simple pass or fail success rate is, well, it's a lot like grading a massive group project without actually knowing who did the work.
Oh, absolutely. I mean, it's an incredibly convenient metric, but it completely obscures the underlying process.
Right. You get this shiny final presentation, the group gets an A+, and you just sort of assume the kid who spoke the most did all the research.
Exactly. When in reality, maybe one person designed the layout, another actually read the textbook, and the one doing all the talking just, read off a teleprompter.
Yeah.
When all you see is that final outcome, the whole internal division of labor is entirely invisible.
And that invisible division of labor is exactly what we're dealing with right now in the world of artificial intelligence. So welcome to today's deep dive.
Glad to be here.
If you're a learner trying to keep up with the overwhelming, frankly exhausting flood of Gen AI research, you are definitely in the right place. Today we're digging into a really fascinating paper from researchers Xian Xin and Hongui Zheng at Peking University.
Yeah, and it's a foundational paper because they're proposing a pretty radical idea. To figure out who is really doing the work inside an AI, we have to quantify system intelligence not in grades, but in bits.
In bits, which is, well, it's a huge shift.
Yeah.
Because as these models evolve, they aren't just isolated predictors sitting in a void spitting out text anymore.
Right. They've evolved into complex agentic systems. They use tools, they search the web, they run Python code to check their math.
They interact with the whole environment.
Exactly.
Yeah.
So applying your group project analogy, the core question is, did the AI model itself actually get smarter, or did its search tool just happen to hand it the exact right answer?
Right. Did the neural network actually solve the calculus problem, or did the calculator tool it was holding do all the heavy lifting?
And if we just look at the final pass or fail grade, we have absolutely zero idea.
None. So we need to unpack how we actually figure out who did the work.
Well, the researchers introduced this brilliant paradigm shift. They argue that to truly measure system intelligence, we shouldn't be looking at absolute success rates at all.
Okay.
We should be measuring data compression.
Wait, okay, compression. Because when you say compression, my mind goes straight to, like, a zip file sitting on my desktop. Are we saying an advanced multi-billion parameter AI agent is just a glorified file zipper?
I mean, it sounds crazy, but the connection between intelligence and compression goes way deeper than just making files smaller. The underlying math of intelligence and data compression are actually two sides of the exact same coin.
Really? How so?
It traces all the way back to classical information theory. The foundational concept here is literally compression is intelligence.
Okay, I am definitely going to need you to walk me through the mechanics of that.
Yeah.
How does compressing data equal being smart?
Let's frame it around the idea of residual uncertainty, or surprise. In information theory, the amount of data you need to send a message depends entirely on how surprised the receiver is by the info.
Right, like how much new stuff they're learning.
Exactly. Imagine I want to describe a highly complex situation to you. If you're already incredibly knowledgeable about the context, say we're both experts in a specific scientific field, I don't need to spell out every single fundamental law of physics.
Right, you just skip to the good stuff.
Right. I just give you a tiny hint, a shorthand, and your brain fills in the rest. The smarter the receiving system is, the shorter the actual message I have to send. And in computer science, we measure the length of that message in bits.
Okay, that makes total sense. Like, if I tell you the sun rose in the east today,
Yeah.
you aren't surprised at all.
Not even a little.
It takes almost 0 bits of actual new information to process. But if I tell you the sun rose in the west, that violates your whole internal model of the universe.
Right, you need a lot more data, a lot more explanation to process that.
So under a fixed task, a stronger AI system allows a target object, like a correct answer, to be reconstructed using fewer bits of information.
Precisely. If we look at a bare AI model, one that uses zero external tools, that's just a special case of this concept. It's relying entirely on its own internal brain.
Just its raw neural weights.
Exactly. But when an agentic system uses external tools, rules, and environments, it moves a lot of that heavy lifting out of the individual message and into the shared system.
Okay, because the tools provide a rigid structure.
Yes. Because that structure is already handling parts of the problem, the residual uncertainty drops, and the number of bits you need to transmit drops right along with it.
Which means we can finally measure exactly how many bits of work the search tool did versus how many bits the core model did. We're literally pricing the intelligence of the system in bits.
So that is the exact takeaway.
But here's the roadblock my brain hits. AI isn't a deterministic calculator, right? You ask it a creative question twice, you might get two entirely different answers.
Oh, for sure. It's inherently somewhat random.
So if we're judging intelligence by counting exact bits, how do we lock down an AI's, chaotic outputs to measure them mathematically?
Well, the researchers solved this by designing a three-part toolkit. It's an executable, strict compress-decompress protocol. It basically functions as a set of rules for how the encoding side packages the data and how the decoding side unpacks it.
Okay, let's break those tools down, because the actual mechanics really matter here.
Tool number one is arithmetic coding. This is the foundational method you use when a specific output has to be encoded exactly, character for character.
Like if you need the AI to produce a very specific string of text.
Exactly. Arithmetic coding takes the model's token-by-token predictions and turns them into a code length by measuring what we call the negative log likelihood.
So negative log likelihood is basically just the math formula for that surprise factor we talked about earlier.
You got it. The algorithm calculates the probability the AI assigns to the correct next word. If the model is highly confident and predicts the word easily, the log likelihood is high.
Meaning the surprise is low.
Right, so it costs very few bits to encode. But if the model is completely guessing and gets it right by pure chance, the surprise is massive, and the bit cost skyrockets.
Okay, that handles scenarios where we need an exact word-for-word string. But honestly, most of the time, we don't care about the exact phrasing.
Right, usually you just want the right answer.
Yeah, like if I ask an AI for the capital of France, I don't care if it says the capital is Paris or Paris is the capital. I just need a successful answer.
And that brings us to tool number two, which is seed coding. You deploy this when there are many qualifying outputs that could solve the problem.
Okay.
Because AI models use random seeds to generate their varied responses, the encoder essentially acts as a prospector. It searches through a predetermined budget of different random seeds, generating answer after answer.
Until it hits one that works.
Exactly, until it finds one that satisfies the success criteria. And once it finds a winner, it doesn't transmit the entire textual answer. It just transmits a tiny fixed-length code representing the rank of that successful random seed.
Oh, wow. So instead of sending a giant paragraph of text, the system just says, hey, decoder, use random lottery ticket number 5. That specific seed gets the job done.
That is the perfect way to visualize it. But seed coding operates under one absolute unbreakable rule: replayability.
Meaning what exactly?
Both the sending side and the receiving side have to share the exact same environment, the exact same model weights, and the exact same tools.
Because if they don't, telling the decoder to use seed number 5 will produce completely divergent results.
Exactly. It would be total nonsense on the other end.
But wait, if arithmetic coding is for exact matches and seed coding is essentially pulling lottery tickets until you win, what happens if the AI just strikes out entirely?
Like, it just can't find an answer.
Yeah. What if the problem is too hard and none of the random seeds produce a correct answer? There has to be some sort of structural failsafe.
And you've just deduced the need for tool number 3, the fallback. It functions as a simple one-bit selector.
It's like a tiny one-bit emergency trapdoor.
A trapdoor is a great analogy. If the encoder searches through its entire allotted budget of random seeds and can't find a single successful output, it triggers this one-bit switch.
And what does this switch do?
It tells the decoder, seed coding failed entirely. Abort the search. We're falling back to manual arithmetic coding to force an exact match.
Oh, that's smart. That elegant little addition ensures that every single sample in a dataset can be encoded successfully, no matter how hard the task is.
Exactly. It guarantees the math always works.
Okay, so we have the theoretical toolkit, but theory is only useful if it holds up in the real world.
Right.
For you listening, you probably want to know what this actually looks like in practice. And reversing text is a really good sanity check here.
Yeah, reading a sentence backward is notoriously difficult for language models. It shatters all the statistical patterns of language they were trained on.
So the researchers used a model called small LM2 360M and asked it to compress reverse text.
And when the bear model tried to compress the reverse text natively, relying purely on its own neural weights, it struggled immensely. It took 2.877 bits per byte to encode the data.
Which is a lot.
It's a lot. But then the researchers gave both the encoder and the decoder a shared deterministic reverse tool. It's nothing more than a simple script that flips the text back to normal before the AI processes it.
And the result was staggering. The code length plummeted from 2.877 to just 0.742 bits per byte. The simple reverse tool saved over 2 bits of uncertainty per byte.
That's a massive drop.
And this is the part that really grounds the concept for me. That 0.742 bits per byte actually beats standard ZIP compression.
Yeah, that's the wild part.
Just by giving the AI a basic mechanical tool, it transformed into a world-class compressor for that specific task.
Which completely validates the core thesis. The intelligence required to solve the problem wasn't living in the neural network's weights. It was embedded in the tool.
Right.
The tool provided the structural logic, which instantly reduced the residual uncertainty.
Okay, so reversing text is a neat trick. But language is inherently messy and subjective. What happens if we test this framework in an environment governed by absolute, unbreakable rules, like, say, a chessboard?
Chess is the perfect closed system for this. The researchers looked at standard algebraic notation, which is just the standard text format used to record chess games.
Okay.
If you just treat a list of chess moves as plain text and ask the AI to compress it, the system expends a massive amount of energy.
It takes 9.828 bits per move, because the AI is constantly wasting cognitive energy considering utterly impossible moves, right?
Right, like a pawn sliding sideways or a knight moving diagonally.
And this is just predicting the next text character. It doesn't actually understand the physics of the board.
Exactly. So to fix this, they plugged the model into a rule-based Python chess environment. This environment acts as an absolute filter.
How does the filter work?
Well, at every single turn, the Python code looks at the state of the board and tells the AI, forget all other text possibilities.
Yeah.
Here is the strict menu of the only legal moves currently available.
And by confining the AI to only those legal options, the code length drops down to 6.545 bits per move.
Yeah.
The environment itself mathematically provided over 3 bits of intelligence.
The environment is literally doing a third of the cognitive work. The AI doesn't have to learn the rules of chess. The environment enforces them, which drastically reduces the surprise of the next move.
That is a beautiful, clean metric.
Yeah.
But let's look at where this metric becomes absolutely critical for the future of science, because they also tested this on complex protein sequences.
Right, and in hard science like protein generation, incremental progress is often completely invisible to standard metrics.
Yeah, let me give an analogy for you listening right now. Imagine you're a developer building a new structural feature for your AI. You run a massive test, and the success rate stays flat at 0.001%.
You'd probably think you failed entirely.
Exactly. You look at that microscopic number and conclude your feature is totally useless. But evaluating an AI like that is like measuring someone's progress in a gym purely by asking, can you lift 500 pounds? If you train brutally for 6 months and go from lifting 100 pounds to 400 pounds, a strict pass-fail metric says you failed both times. It records 0 progress.
The pass-fail metric just has 0 resolution for incremental capability. So in the protein experiment, the researchers wanted to see if giving the AI a calibrated homologous template,
Which is essentially just a structural blueprint of similar proteins.
exactly, a blueprint. They wanted to see if that template would help it reconstruct the missing masked parts of a sequence. If you evaluate the bare model without the template using standard absolute success rates, it essentially flatlines.
It looks like 0 progress.
Yeah.
With the 100-pound lift.
But when you switch the lens and measure the intelligence in bits, a completely different story emerges. The bare model required 200.65 bits per sequence to encode the missing residues. The uncertainty was massive.
Right.
But when they introduced the calibrated template, the code length dropped to 116.88 bits.
Wow. The bit metric proves that the template tool was functioning perfectly. He was doing massive amounts of heavy lifting by reducing uncertainty by nearly 84 bits per sequence.
Exactly.
Even when the absolute success rate looked like a failure, the bits proved the AI was getting significantly stronger. It just hadn't hit that 500-pound lift yet.
And that provides a real quantitative lifeline for developers. They can finally measure the marginal value of every single tweak they make to a system rather than just flying blind.
That is massive for scientific research. But let's bring this out of the lab and connect it to something you probably use every single day.
Okay.
Asking an AI a question and letting it search the web for documents, retrieval augmented generation, or RAG.
Right, RAG is everywhere now. The researchers analyzed this using a data set called Hotpot QA and a model called Quen3.5. Their goal was to isolate and price the specific value of the retriever tool.
Okay.
If you disable the retriever and force the model to answer blind, pulling facts entirely from its own internal memory, it takes 24.46 bits to compress the correct answer.
But if you hand the model gold documents, perfectly relevant, highly accurate info retrieved from the web, The code length plummets to just 6.17 bits.
It's a huge improvement.
The presence of relevant documents saved over 18 bits of uncertainty. But here's the twist that absolutely blew my mind. What happens if the retriever tool is terrible?
Yeah, this was fascinating.
What if it searches the web and hands the AI distractor documents filled with completely irrelevant information?
Well, common sense dictates that garbage data harms the model's performance. You'd assume it adds noise, increases confusion, and drives up the bit cost.
But the data completely defies that assumption. Irrelevant documents aren't universally useless. Out of 100 questions tested, the distractor documents actually helped the AI on 76 of them.
And saved an average of 2.95 bits.
This forces us to ask a deeply counterintuitive question. How on earth does garbage data help an AI compress the correct answer?
The paper suggests it comes down to a priming effect. Even irrelevant documents often contain a similar topic prior.
Okay, to visualize this, it's like I'm trying to remember the capital of a specific state. If I start talking about totally irrelevant things like snow, mountains, and skiing, your brain is already warming up the neurological pathways for a place like Denver.
Right, exactly. Even if every specific fact I'm saying is completely wrong, the vocabulary and the context prime the neural network's attention mechanisms, pointing it in the general direction of the right answer.
That offers such a profound insight into how these models process context. Their pattern-matching engines and even adjacent patterns reduce surprise.
Furthermore, the most realistic real-world scenario isn't pure gold documents or pure garbage documents. It's a messy mix of both.
Right, a normal web search.
Exactly. When they fed the AI a mixture of gold and distractor documents, simulating a standard search, the system still saved 17.13 bits.
Which mathematically proves that as long as the relevant evidence is buried somewhere in the context window, the model is remarkably resilient. It can pick out the needle of useful info from the haystack of trash.
Yeah, it's incredibly robust.
And more importantly, we can now put a precise price tag on the value of that retrieval tool. In this specific setup, the ability to search the web is worth exactly 17.13 bits of intelligence.
So we spent a lot of time analyzing how tools and environments change the bit count. But this brings us to a fascinating turning point in the methodology. Who actually grades the test?
Right. Who decides if the AI's answer is correct enough to trigger a successful seed code?
Grading on a curve. The researchers tackled this using a dataset called tiny stories. They looked specifically at what they called observation granularity.
Basically, they wanted to see what happens when the judge gets stricter.
Exactly. They constructed what they term a semantic observer ladder. At the very bottom rung of this ladder, the judge is incredibly lenient. To be considered a successful reconstruction of a story, the AI only has to preserve the names of the original characters. Nothing else matters.
Because that is such a low bar, almost any random seed will stumble into getting the characters right. The acceptable set of answers is huge, so the code length is very low.
But as you climb the semantic ladder, the judge's criteria become aggressively stricter. On the next rung, you have to preserve the characters and the main conflict.
Okay.
Climb higher, and you need the characters, conflict, and specific events. At the very top rung, you must preserve all of that and the exact original ending.
And the data reveals that as the grading gets stricter, the code length strictly and monotonically rises.
Yep.
The acceptable set of answers shrinks dramatically, meaning the AI has to search much harder and burn more bits to pin down the exact right story.
Which proves that you can't just throw out an intelligence score in a vacuum. A system's intelligence is entirely dependent on how aggressively you define success.
And this dynamic leads perfectly into the final, and maybe most commercially significant, finding of the paper: the compute trade-off.
This is the million-dollar question.
Literally. For companies deploying AI, compute budget equals actual money. So for anyone listening who manages or builds these systems, the practical question is, does this mean if I just throw infinite money and an infinite server budget at an AI agent, it will just infinitely keep getting smarter and compressing data better?
To answer this, the researchers plotted what's known in economics and engineering as a Pareto frontier. It maps the trade-off between resources spent and capabilities gained. And the definitive answer is no. You cannot brute force intelligence indefinitely.
So using the tiny stories data, they tested this by expanding the encoder's budget of rollouts, right?
Right. Basically, they gave the AI more attempts to draft a summary and search for the best one before forcing it to pick a winner.
And when they increased the computational budget from one single attempt to 64 attempts, the initial compression gains were dramatic. The code length dropped from 292.1 bits all the way down to 127.5 bits.
So initially, throwing more compute at the problem does buy you a smarter system.
It does. But they hit massive, crushing, diminishing returns. The data shows that the semantic path rate, which measures how often the system succeeds using the highly efficient seed coding, rather than falling back to the raw, expensive arithmetic coding, it saturates rapidly.
Yeah, it flatlines around 8 attempts.
Going from 1 attempt to 8 attempts gets you almost all the actual intellectual benefit. Going from 8 attempts to 64 attempts just burns a massive amount of electricity and server costs for a microscopic, practically useless reduction in bits.
The compute code length curve exposes the harsh physical realities of artificial intelligence. Intelligence isn't just a static number a model achieves in a lab. It's a highly constrained curve that depends entirely on how much energy you are physically willing to spend to search for the right answer.
There are hard ceilings to scaling.
Absolutely.
Let's tie all of this together for you listening. Why does this deep dive matter? Why should you care about marginal bit value or negative log likelihood? Because this framework fundamentally changes how we evaluate the future of technology.
It does.
It proves that giving an AI an agentic workflow, giving it a web browser, a Python environment, a calculator, isn't just a quirky implementation detail or a neat user interface.
It is a fundamental change of description language. It transforms our understanding of where the capability actually resides.
It gives us a public accounting unit. We can finally look at that massive AI group project and say, with mathematical certainty, the core neural network did 120 bits of work, the web search tool did 17 bits of work, the strict grading rubric cost us 40 bits of efficiency, and adding more server compute beyond 8 attempts is a waste of money.
Right, we can finally see exactly where the intelligence lives.
That unprecedented level of precision is going to change how every major system is engineered from the ground up. It allows developers to allocate resources exactly where they yield the highest bit reduction.
It really is a paradigm shift.
It is. But before we wrap up today, I want to leave you with one final kind of mind-expanding concept pulled right from the very end of this paper. The researchers call it agentic pseudo-entropy.
Oh, I love this part. It is a beautiful, deeply philosophical concept disguised as mathematics.
The idea is this. If we fix the task, fix the core model, fix the environment, and give an AI system absolutely all the optimal resources and infinite compute it could ever ask for, there is still a baseline number of bits that simply cannot be compressed.
Right. There is a hard floor you cannot drop it.
It represents the residual uncertainty that no tool, no environment, and no amount of raw computational power can ever erase.
Okay.
So here is a lingering thought for you to explore on your own today. Does this leftover, uncompressible number represent the absolute hard limit of artificial intelligence, a ceiling we will never break through? Or does it represent the fundamental, irreducible complexity of the universe itself?
Wow.
Some things, human emotion, true randomness, the chaos of reality, are just incredibly messy, and maybe no algorithm, no matter how advanced, will ever be able to compress them down to zero. Thanks for joining us on this deep dive.